So here's a second example that we can use the reference circle to solve. So in this example we have a pendulum bob. Bob is just the word for the thing that we're hanging at the end of a string. So we have a pendulum bob swinging back and forth in simple harmonic motion. Its amplitude is 0.1 meters, so that's amplitude. I'll just zoom in a little bit more here. And its period is 0.6 seconds, so that's period, t. And at time equals 0, the pendulum bob passes the equilibrium position, moving to the right. So firstly, we're asked, what is the angular frequency of this motion? So we know that omega is equal to 2 pi over t, which in this case is 2 pi over, and the period here was 0.6 seconds. And we can calculate that. So 2 times pi divided by 0.6, that gives us about 10.5 radians per second. radians per second. Okay, and then we are asked, where will the pendulum bob be after 0.1 seconds? Because here we now want to draw a reference circle. So let's draw a circle here, and then we'll draw the pendulum. So the pendulum is going to swing from its extreme position on this end, and then it's going to swing through equilibrium, and then it's going to swing to its extreme position at this end. And this is time equals 0 here. And so if the phasor is spinning anti-clockwise, we would draw it here to start off with, and then it's going to spin that way. Okay, so we know that the period is going to take 0.6 seconds to go all the way around, which means that in every 0.15 seconds it's going to complete a quarter cycle. So 0.10 seconds, so we have t equals 0.10 seconds. We know that the amplitude was 0.1 meters. And we now know that omega is 10.5 radians per second. Okay, so it's going to go 2/3 of the way up to here, because that's 0.15 and this is 0.10. So we can sketch in the phasor here. It's going to be something like that. And so the position of the pendulum at this moment will be in line with that point, so it'll be here somewhere. And we're interested in finding this distance, x. Okay, that distance x in our reference circle will be this distance here. So that's x. And we know that this angle here is the distance, the angular distance that the phasor has gone, which is omega t. And we also know the amplitude here. The amplitude was 0.1 meters, so that's the length of the phasor, or the hypotenuse of our triangle. So in this situation, we want to find the opposite side of the triangle. We know the hypotenuse, and we can know the angle. So we can write x over 0.1 is equal to sine of omega t, which was 10.5 is omega, and the time that's elapsed is 0.1 seconds. So x is going to be equal to 0.1 times sine of 1.05, which is just 0.1 times 10.5. So that's what we need to figure out. So 0.1 times 1.05, and I am in radians, and we want to take the sine of that, which gives us 0.0867, or 0.087 meters. So it's almost out at its maximum position, which was 0.1, but not quite. Okay, so the next part, where will the pendulum bob be after 0.20 seconds? So let's look at that one. So once again, we'll copy this diagram. And once again, we have the pendulum bob, and it's now 0.20 seconds. So let's draw the pendulum bob at these 3 positions again. I'm going to try to line this up with the one above. Will it line up nicely? No, it won't. Okay. So we're going to start off here, and it's going to spin. Remember, it takes 0.15 seconds to get to here, so now we're interested in t equals 0.20 seconds. We again have a equals 0.10, and we have omega equals 10.5 radians per second, and that was meters. So again, we can draw the pendulum bob in these 3 positions here, just to give a sense of what's going on. So it's going to swing all the way out to there, and then come back some. So it's going to go all the way up to a quarter. That takes 0.15 seconds. Then it's going to go a third further, so it's going to end up about there. So we can draw that there. So we're interested in how far from the equilibrium position it is at that time. Is that the question? Let's just have a look at the question again. Where will the pendulum bob be after 0.2 seconds? Okay. So we do know that the time that it takes to go through here is going to be 0.05 seconds, because the time that it takes to go to that point is 0.15 seconds. So this little time, so we'll write omega t here, that time is 0.05 seconds to find that little angle there. So omega t for that is going to be 10.5 times 0.05. So that's 0.525. radians. Okay, so now what are we actually interested in finding out? What we're interested in finding out is how far is it from equilibrium at that moment. So that's just this green distance here. So it will have swung all the way out and then come back a little bit. So it'll be here. Okay, that's x that we're trying to find out. Okay, so now this is the adjacent side of the triangle. We know that the amplitude is 0.10, that's the length of the phasor. And so we know we want the adjacent side, we know the hypotenuse. This is going to be a cosine. So we can say 0.1 over x. No, it's the other way around. It's adjacent over hypotenuse, so let's do that again. So 0.1, no, sorry, it's x over 0.1 is equal to the cosine of 0.525. So x is equal to 0.1 times the cosine of 0.525. 0.1 times 0.525, and then we'll take the cosine of that, and that gives us 0.087 again. So in this case, it's again 0.07, but this time the pendulum bob is on its way back. So it's swung out to 0.087 after 0.1 seconds, and then it's swung out to its furthest position, and it's come back by the time 0.2 seconds have passed. Okay, let's look at the fourth one. How long will it take the pendulum bob to reach a position 0.05 meters to the left of equilibrium? All right. So let's copy this and let's pop it here. Alright, so now what we're interested in is 0.05 meters to the left of equilibrium. So again, it's starting here, and it's going to go 0.1 meters to the right of equilibrium, and then it's going to come back to 0, and then it's going to be halfway in between, so it's going to be like here somewhere, and this distance here. So we'll draw the pendulum bob at the bottom here. So it's going to go from there all the way out to there, all the way back, and then it's not going to go all the way out to here, but it's going to end up in this position, and we want to know how long it took for it to do all of that. So it's going to have gone all the way out, all the way back, and ended up there. Okay, so that is the time that corresponds to this angle here. And we know that that time, the time that it takes to complete a full half cycle, is going to be exactly half the time period. So if we can just work out what this time is, then we will know how long it took. So it's going to take so the time taken, so we can call this little green time here, will be t over 2 plus little green t. So let's find little green t. Well, what do we know about this situation up here? We'll again use our trigonometry to do this. So we know, for example, that this is 0.1, that's the amplitude, that's the length of the hypotenuse of this triangle here. And we also know that it is 0.5 meters away from equilibrium. That distance there has got to be 0.5 meters, because that's where we were interested in. So this is 0.5, oh, it's not 0.5, 0.05. This is 0.05 meters. So let's just draw that triangle again, because it's gotten a little bit messy and small there. So if we take that triangle here and we'll draw it again, we'll go this distance here is 0.5, oh sorry, 0.05. This distance is 0.1, and if we can only figure out what that angle is, then we will know how long it took. So theta is equal to, well, we know this is the opposite side and this is the adjacent side, so it's going to be the inverse sine of 0.05 over 0.1, which is 0.05 divided by 0.1, and then we take the inverse sine of that and we get 0.52. 0.524. But that angle theta has got to be equal to omega t. So t is equal to 0.524 over omega, which was 10.5. So we'll just divide this number by 10.5, which gives us 0.05 seconds. Is that right? Yeah. Okay, so then it's going to be a half a period plus 0.05. And what was the period? The period was 0.2 seconds, was it? No, 0.6 seconds. So t total was half a period, which is 0.3 plus 0.05, which equals 0.35 seconds. So that's how long it takes for the pendulum to swing all the way out to the right, all the way back to equilibrium, and then another 0.05 meters to the left of equilibrium. Okay, one last question. Where would the pendulum bob be 0.15 seconds after reaching the far left position. Okay, so one more problem here, and we'll paste that. This is part 5. Okay, so now we're interested in where it will be 0.15 seconds after reaching the far left position. So now we're interested in where it will be after being at this position. So we're going to have our starting phasor here now, and we're going to go 0.15 seconds later. So we know that 0.15 seconds is exactly a quarter cycle. So this is actually reasonably easy. It's going to be exactly at equilibrium position. So we can say it will be at equilibrium position. So where we put our starting phasor depends on what the starting point is of our motion. So in this case, we would have put our starting phasor, or we did put our starting phasor pointing straight to the left, because we were interested in what was happening after starting at this far left position here. Okay, and we know that we can say as 0.15 seconds is 1/4 cycle.